So where to begin? I think, at least some of you here are kind of repeat customers. You must have been here and heard about dark matter in other contexts, and probably most of you have heard about it from astronomers. So I want to tell you a little bit about it from the perspective of a physicist and kind of complete the picture. And we'll have several types of dark matter to talk about, but let me just start. And I'll start with an analogy. So let's say you're just sitting at your home kind of peacefully, and then it kind of hits you. I wonder how much my house weighs. So you want to put it on a scale, and in very convenient units, you expect it to weigh about one house. And so you do the experiment, you put it on there, and you find that contrary to your expectations, actually it measures not one but 6 house. Okay, and of course, the first thought that should cross your mind is maybe there is something wrong with the scale. So you have to check the scale, you have to make sure there's nothing wrong with it. And you do that, you do a lot of tests on the scale, you make sure it's operating correctly, but eventually you reach the conclusion that really the scale is working right. So there is something going on, and at that precise moment, your scientist friend comes into the room. I'm sorry, something went wrong with my emojis there, but your scientist friend says, hey, I think your house coexists with 5 other ghost houses that weigh exactly the same amount, and that's why the scale is showing 6 house. Since you don't have a better theory than that one, you kind of have to live with it, and your scientist friend is over there feeling kind of all pompous. But if you're a sane human being, which I'm sure you are, you would be much happier with that kind of proposition if you can confirm the existence of these ghost houses on top of yours in some other way. For example, if you somehow sometimes saw a vase being kind of knocked off a table, or hearing strange sounds at night, etc., you might be better convinced. So that's basically, as you can guess, the analogy here is all about dark matter. So this is us in our little galaxy, but we find that whenever we look at gravitational effects, there just seems to be a lot more mass to our galaxy and to other galaxies out there, and we can't really account for it in any other way. We've checked that we're not getting gravity wrong. We seem to be getting gravity right, and so there really seems to be all this extra mass out there, and for the lack of a better name, we call it dark matter. I don't know if we gave a name to it. If I was the one giving a name to it, I probably would have called it transparent matter, because light really passes through it, does not get absorbed by it. So dark matter is a little bit deceptive, perhaps, or ghost matter. If you just want something cool, you could do that. So as a physicist, though, I'm here to tell you, what does it even mean? How can this mysterious substance be there and we not feel it? How does it coexist with us, and what would it mean for it to interact with us, so that if I wanted to convince myself that, if I wanted to see in the analogy a vase being knocked over or hear strange sounds, how would that work? And to walk you through that, I have to give you a little bit of an intro to particle physics. And so just the very brief message here is that the foundation of particle physics is this framework that we call quantum field theory. And quantum field theory is a complicated beast. It took actually some of the best minds of the 20th century to kind of bring together the theory of special relativity from Einstein and the theory of quantum mechanics together to eventually create this framework called quantum field theory. It takes a while to really explain it in detail, which I won't do. So I'll give you a crash course, but suffice it to say, if you want to take anything away from this particular talk, one thing you can take away is everything, and I mean everything, is energy traveling on field. So it turns out, in the universe, there's a constant amount of energy, and that energy exists in various forms on what we call fields. And it can change from one field to another, but the amount of energy never changes. So let me go into a little more detail on that. So here's rule number 1. What is this thing called field? So just imagine some medium on which energy can exist and on which energy can propagate. So if you want to visualize it as maybe a network of springs and masses. So if you pluck one of these masses, right, and you let go, it'll start oscillating. That disturbance may spread over this network of springs. So think of this as this everywhere filling field. Okay, this is a visualization for it. And as it turns out, there are fields for every type of particle. So there's a field for electrons, there's a field for what we call photons, which is a particle of light, and any particle you've ever heard of exists on its own field. And there can be energy propagating on these fields. So that's rule number one. Rule number two, energy can go from one field to another. Not from any field to any other field, but there are a set number of pairs of fields that can exchange energy. There's a little bit of fine print here. For example, if there's no energy at all on, say, an electron field and you want to put energy on there, you kind of find yourself forced to create a pair of particles. Just one won't do. You have to create a pair, and one is, in fact, in some ways, an mirror image of the other. We call it an antiparticle. You have to create a particle and an antiparticle. But that's a level of detail that will only be important in a couple of slides. Rule 3, so if you do put enough energy on a field, you can make a ripple, and that ripple will go down the field, and that's basically what we call a particle. So when I say an electron has gone from here to here, what's really happened is that a bunch of energy started over here on a field, propagated to over there. Okay? So everything, all kinds of particles, all kinds of matter that you know is energy on a field. But there is even more than that. Even forces between particles are still energy between fields. Everything, like I said, is energy on a field. Rule 4, even if you put not quite enough energy into a field that it cannot make a ripple that can propagate, nevertheless, the field can hold on to it for a while and pass it along. So some fields can act as intermediaries, take a certain amount of energy from one field, give it to another field, without themselves making particles. Okay, so give yourselves a hand now. You've mastered quantum field theory. So moving along. So this is, even something like what looks like empty space can be a very dynamic environment in the language of quantum field theory. So this is, I believe, the inside of basically an atomic nucleus, and this is the energy kind of just jumping from place to place on these fields. So these fields are very, very dynamic objects, and energy just moves around on them. This is obviously a simulation. We cannot see down to distances of atomic nuclei with our natural eyes. Okay, so basically if you want to describe the universe, in fact, either it's this universe or any other hypothetical universe that you want to think about, you can do so by basically specifying a number of fields and say, these are the fields that permeate this universe, and here are pairs of them that can exchange energy. Okay? So once you've specified your fields and once you've specified which ones can exchange energy with one another, you're done. You've described the universe in a quantum field theoretic context. All right? Now, I can't draw multiple fields on top of each other if I keep using these masses and springs, so I'm going to simplify things quite a bit. I'm going to go from a three-dimensional representation to a single-dimensional representation. So think of this little line as basically a field filling all of space, and when there's energy on it, I'm just going to put a bump on top of the line. All right? So what do I mean when I say forces even are energy that propagate on fields? So let's imagine, for example, the force of electricity, right? Electricity is a force, and it's communicated by a field. It's called the photon field. This is also the particle that is responsible for light. So when you look onto the screen or into any of these lights, there's a photon that starts as a ripple at that source, propagates on that photon field, and enters your eye. So here we see basically two electrons. You see the bumps, so they're ripples traveling on that electron field. So they're electron particles. They're moving towards one another. This field coexists with the photon field. They're on top of one another. Right now, there is no energy on the photon field. The electrons are moving towards one another. But at any given time, one of the electrons can decide to give some of its energy over to the photon field. The electron is allowed to share its energy with the photon field. So now some of that energy is on the photon field. It can propagate to the right. In the meantime, think of what happened to the electron. It's like if you had, a heavy ball and you threw that ball really hard towards your friend, you might, get a little recoil, right? So the original electron that threw that photon away gets a bit of a recoil, turns around, the photon, the energy on the photon field travels and is caught by the second electron, which until this point has been unaffected, and now that one catches it and recoils a bit as well. So it flips its direction, and now all of a sudden you have these two electrons that were originally moving towards one another, now moving away from one another, because they've exchanged some energy via the photon field and then basically acted as a repulsive force. Okay, so even forces, not just matter, but even forces can be thought of as basically energy propagating on fields. Now, it can do much cooler things than that. For example, now let's imagine again a pair of electrons. In fact, I'm going to take an electron and on an anti-electron, what we call a positron. Let's say they move towards one another. And let's also imagine now on top of the photon a third field of a new particle that you never heard from. You never heard from it because it doesn't exist in the natural universe. Okay, it is too short-lived. It's all gone. It may have existed at the beginning of the universe, but it's all gone now. Okay, so there's no energy. Whoops, there's no energy on that field at all. Right now, there's no energy on the photon either. But when the electron and its antiparticle come together, they can collect all their energy, completely vacate the energy from the electron field, and give it over to the photon. The photon will hold on to it for a while, but if this new exotic particle is charged, it will talk to the photon. Basically, the rule is anything that carries charge will talk to the photon. So the photon can now give the same energy over, not back to the electron field, but into the exotic new field and make a particle-antiparticle pair of this exotic particle. So this particle that didn't exist since the beginning of the universe, you've succeeded in making a pair of it, but by basically colliding two electrons together really fast, and that energy leaked through the photon field to create these exotic particles. Okay? This is exactly how we make new particles at places like the Large Hadron Collider. We use the particles that we can control, we smash them, that energy gets converted and transmitted via some of our force-carrying fields into hopefully exotic fields that we've never even heard of before. Okay? Now, how does that matter for dark matter? Well, dark matter is an exotic field. Okay? And so we could hope to make our own dark matter. If we collide particles, we might be able to, so the blue will stand for particles that we can control, we can collide, so that energy can leak via some intermediate particle down to the dark matter field, and we can make pairs of dark matter particles. The catch here is that you cannot use the photon as an intermediate particle. Dark matter, by its very nature, is not charged. It's, it doesn't talk to the same forces that our particles, the particles that make us up, like the electron, they talk to some forces, but the dark matter doesn't. That's why dark matter can coexist with us, that, why I can push through probably a bajillion dark matter particles that occupy the same space. That's how we can co-occupy the same space, because these fields do not readily exchange energy with one another. But if there is any kind of intermediary at all, this pink field, whatever it may be, it may only transmit the energy over with a very low probability, once in a trillion times, once in a gajillion times. But if you keep at it, you might be able to make some dark matter particles and look for it. So that's one of the ways that we hope to search for dark matter. It's not the only one. Here is another idea. You could imagine, after all, you don't have to make a new dark matter particle. It's already around us. There is tons of dark matter particles that fill the universe. So you can imagine that one of these dark matter particles may decide to give some of its energy again to some intermediate field that can then kick a visible particle around that was just sitting there before. So you have a particle, a visible particle, a normal particle, just sitting there, and after a while, it just gets a kick out of nowhere. And you wonder, well, how did that happen? It's possible that a particle that you did not communicate with readily imparted some energy and some momentum onto it. Okay? This is called the method of direct detection. As you can imagine, the catch here is that, of course, by the way, this is in my analogy from before, this is the vase getting knocked over, right? A visible thing all of a sudden just getting a kick out of nowhere. And the catch here, is that there are many things that can kick electrons around. You have to make sure that truly you've ruled out all other possibilities before you decide that there is something truly new going on. So that's why these experiments that look for dark matter in this way, here's an example of it. It's a very pure material, shielded from lots of external effects by basically being placed way underground. Typically people use abandoned mines for this kind of thing. So you put that experiments down there, you shield it very well, and if one of your particles nevertheless gets a kick out of nowhere, you get a pretty good idea that something interesting has happened. So that's the second way that I'm going to talk about that we look for dark matter. And the third way is that maybe you don't even have to wait for dark matter particles to come to you. After all, if space is filled with these dark matter particles, every now and then a pair, particle-antiparticle pair of dark matter particles may just collect its energy and give it over to our regular particles. So this would be annihilation of dark matter particles and creation of visible particles. So you might find that out of nowhere come these really energetic particles that you can look for, and we have tons of experiments that look for that kind of thing. We have space-based telescopes that look for very high energy particles emanating from places like the center of the galaxy, and so forth. And this we call indirect detection. And if you think about it, if you think about the various ways in which a visible normal field can feel the effects of a dark matter field, these three pretty much span your possibilities. Okay, so these are the ways that we look for dark matter as a particle. Remember, we know it's there from its gravitational effects. That's the house on the scale, right? We know it's there, but we would like to find a direct way of communicating with it. That's what the particle physics part of it is about. And so these experiments give us a way to look for those effects. So the next thing you should ask me is, okay, but why are you so optimistic? I mean, we know that there's dark matter out there, but how do we even know that there is an intermediary field? Maybe dark matter never exchanges energy with us, and so it'll exist by itself for all of time, and we will exist by ourselves for all of time. And apart from gravitationally attracting one another, we will never feel the effects of dark matter. Isn't that possible? Or maybe the mass of a dark matter particle is so heavy that just making a ripple on this field takes so much energy that our technology will never allow us to do that. Right? So you could ask me, how do I know that those scenarios are not the case? And the answer is, well, actually they could be. So for all we know, we might never be able to detect dark matter as a particle. If there is no intermediary field, end of story. Okay? And we don't get to choose. The universe is what it is. We just get to try to understand it and describe it. But there are reasons that lead us to be optimistic. And so in my remaining however many minutes, I'll just tell you a little bit about that. And that has to do a little bit with how many dark matter particles are there. So since I can put my galaxy on a scale, metaphorically, I know roughly how much missing mass there is. So I know how much mass there is in dark matter particles. But what I don't know is it a few very heavy particles, or is it a whole bunch of light particles? So the number of dark matter particles is an unknown. It'll depend on the mass of a single dark matter particle, which we don't know because we haven't discovered single dark matter particles. That's what we're trying to do. However, we can think about how these, whatever number of dark matter particles are out there, how they came to be. So for that, think about the very early universe where it was very hot. Okay, so very early universe, everything carries a lot of energy. Okay, so there's tons of energy propagating on visible fields, tons of energy propagating on dark matter fields. Everybody's exchanging energy with everybody, and everything goes. So particles can destroy one another, make dark matter particles. Dark matter particles can destroy one another, make regular particles. Okay, a lot of fun. But eventually the universe cools. Okay, and as the temperature drops, eventually the temperature will drop enough that there's now no more enough energy on these fields to make new heavy particles. You can still make light particles. So if heavy particles collide, you can still make light particles because the energy is already there. But if light particles collide, there may not be enough energy to make new heavy particles. Okay? So this is when the universe has cooled a bit, but not quite completely cold. And at that point, the number of heavy particles, as you might imagine, goes down and down and down, right? Because the ones that exist can annihilate, but you cannot make any new ones anymore. And then eventually, there are so few of them left that they can't even get to one another. And at that point, the number of leftover particles becomes a constant. And they are just floating out there, not being able to find one another, okay? And if dark matter has what we call weak interactions, okay, and that's not just a colloquial usage of the word weak. In the standard model, well, in particle physics, we have something called weak interactions, and that actually has a very technical meaning. It's just got a very specific strength for transmitting energy via these fields. But if dark matter has that property, that it interacts via the weak force, that it is weakly interacting, if it is what we call a weakly interacting massive particle, a WIMP, then you find, by a miracle, that just the right amount is left over. And that's exciting for us because we think already there is something interesting about these weak interactions. And so dark matter having these weak interactions is not a crazy idea. So this is almost a hint, right? All of a sudden, you just realize, maybe you know something about these ghosts after all. So that is just one type of dark matter. There are many others that I'm probably out of time already, so I won't be able to tell you much about them. But so the WIMP is just one of these theoretical ideas that we think about, but there are many other ideas circulating around for possible types of dark matter fields. And it only gets interesting, right, when you have an idea and it solves more than one puzzle. So particle physics has a number of open puzzles. The weakly interacting massive particle, like I said, solves more than one puzzle. It is dark matter, but it's also related to these weak interactions. Some of these other things also do the same thing. For example, what we call axions or asymmetric dark matters connect to other open problems in particle physics, and that gets us excited that we may be onto something. Okay, so I'll leave it here so that we can take some questions. So thank you for your attention.
All right, we have time for a few questions. I saw the one in the back first.
Is there any particular reason within the current framework that there must be a particle, or could it just be that dark matter only gravitational?
So yeah, so that goes back. Let me repeat the question. The question is it possible that dark matter interacts only gravitationally? The answer is yes. That I was sort of alluding to that before. That's kind of the nightmare scenario, but it's certainly possible that dark matter exists. So quantum field theory is kind of the state of the art in terms of how we describe the world. So we do think that dark matter is some sort of particle on a quantum field. That we're pretty sure about. Okay, but whether or not it can interact with us via intermediary fields, anything other than gravity, we don't really know. So there are reasons that give us hope, but we don't know for sure.
Okay, next question. Up front.
Rule number 4, where a particle doesn't have enough energy to move from one field to another, so the force that can allow it to pass through it. We're talking about moving away.
So I would say the particles are the moving waves. So when you can make a wave and it kind of keep going and rippling away, that's a particle. In rule 4, so remember that a field, maybe I haven't really said this very explicitly, but there's a threshold for any given field that if you give it too little energy, it won't make a ripple. If you give it enough, it'll make a ripple. And that threshold is the mass of the particle you're trying to make. Clearly, if you want to create a new particle, you have to put in at least as much energy as the mass of that particle. So if you don't put in enough to make a new particle, to make a ripple on that field that propagates away, the field can nevertheless hold on to it for a bit, but it won't be a wave. It'll just be a lump of energy in that field that exists for a short amount of time before it's transmitted to another field.
All right, next question right there. Mustache.
What do we know about the distribution of dark matter in the universe? Is it clumping in the same way as regular matter?
Yes, that's an excellent question. The question is, what do we know about the distribution of dark matter? Is it completely homogeneous, for example? Does it clump? We don't know for sure in the sense of, exact knowledge, but we have many numerical models and we have many measurements How do we measure such a thing? For example, light bends in the vicinity of heavy sources. So we can see how light bends in situations where we don't see any visible matter. So there's no obvious reason why that light should have bent. Nevertheless, it does. So we can map out, for example, how much dark matter there is. And it looks like, both based on our simulations and on our best guesses, that dark matter tracks regular matter pretty well. There is also lots of dark matter in between kind of galaxies, something that, I mean, I should really give this question over to my astronomer friends, but what people refer to as the cosmic web, strings of basically, dark matter particles in between massive things like galaxies. So there's certainly structure, but if you looked at it from very, very, very far away, so that, the entire universe would only, would be within your field of view, it would look pretty homogeneous. It's only when you start going at it with a magnifying glass at the tiny scale of galaxies, then you start seeing the structure.
That's a good preview for next month. I'll be talking about that next month a little bit in detail. Blue hat in the back.
How is this affected by the fact that the Big Bang theory has kind of become obsolete or incorrect?
Okay, so to repeat the controversial question, gentleman over there says that the Big Bang Theory has become controversial. I would not say that. The Big Bang Theory is... See, I'm sorry, obsolete, yes. So I wouldn't say it is obsolete, although the Big Bang, it's a bit of a funny thing that people talk of the Big Bang as if we know exactly how the universe started. That's the one time in the universe that we know the least about. And in fact, all we know is the universe is getting, as time goes forward, colder and less dense and colder and less dense. So we can play the movie backwards and imagine that the universe gets hotter and denser as you go to earlier times. So, you extrapolate that to a point where everything was infinitely hot and infinitely dense. But that even need not be the case. We know that very, very, very early in the universe, and we're really talking about incredibly small fractions of a second, the universe was, it existed in this exotic phase called inflation, where, the universe is expanding now, but boy, back then, it was just blowing up like nothing you've ever seen. And what happened before then, we have absolutely no direct probe of. And every physical theory has its limitations. And we're a little better than our, say, 19th century colleagues in the sense of knowing a little better where the limitations of our theories are. So going past that point and saying, I know exactly how it all started is a bit of a hubris. So it may have never become infinitely dense and infinitely hot. Before even inflation, there may have been a string of, soup of strings or, membranes or what have you. We don't know. Our theories at some point don't even apply and we can't describe it well mathematically. But when we talk about Big Bang, what we really mean is not so much there was one exact instant where it all began. What we really mean is in the beginning, the universe was extremely hot, extremely dense. And what lies beyond that, we're not sure.
I think that the universe is already shown to be not just expanding, but pulsating, beating like a heart, and that it's actually increasing in temperature.
Okay, so just to repeat, the statement is that the universe may be pulsating. Brandon tells me this is also referred to as the Big Bounce model. To my knowledge, we have no observation of anything like that. It's a theory. It's a cool idea, but there is no reason to think at this point that it is correct. Unlike, the fact that it was very hot and dense in the beginning, that's almost, I would say that is uncontroversial.
All right, we got time for one more right there. Or two more, sorry, two more, but right there.
So, with humans wanting to they have a taking dark matter, its purpose is more so, I'm assuming, the initial purpose would be so that way we can navigate around it in space and stuff like that. Could it actually be weaponized, or is there possibilities?
The question is, can the production of dark matter be weaponized? I'll generalize this a bit and say, can it be useful in any way? The answer is I have no idea. Because it'll depend very much on what type of particle dark matter is, what kind of field it is, what other fields it exchanges energy with, and we don't know. There are models that include dark matter particles and yet other exotic particles, which if that was the right story, would make, for example, generating energy from fusion much easier. Okay, this is a fringe model. I am absolutely not advocating that this is the story, but there's almost an infinitude of stories to choose from, and dark matter could be any one of those, but some of them sure could have even technological applications, although I personally don't think it very likely.
Let's thank Professor Kilić one more time.
Thank you.